right. Welcome, everybody. So this course is going to be sort of an introduction to the subject of unlikely intersections, which is really a subject that's motivated by problems. So somehow, from a very big picture perspective, we'll develop theory like as we need it, but we'll be focused on a specific sort of set of problems and the approaches that are currently known. It's sort of I think it's a good time to sort of look at the subject because there's sort of a lot of things we know, there's a lot of results, there's a lot of techniques, there's also like a plethora of things that we have no idea how to tackle. In terms of sort of background for the course, oh wow, this is really nice hygrometric. So the thing that I think we'll be using sort of a lot, which will be good to brush up on, is Galois theory. A frequent sort of path we'll be taking is we'll be reducing things to arithmetic, and then we'll use the Gallo Group in some particularly clever way that someone came up with. So that'd be a good thing to be familiar with. We'll be using sort of some analysis, but not very much. Sort of Fourier theory, and sort of fairly basic measure theory. And the other thing which we'll sort of call upon as needed, maybe we'll review some of it, is sort of introductory algebraic number theory. This one is not going to be always so necessary, but on occasion it will prove useful. We'll sort of use some other things as we go along. We use some algebraic geometry, we use some homonymity, but we'll review that stuff a lot more once we get to it. All right. Okay, is there anything I'm forgetting that I should be doing because this is the first lecture? Any first lecture questions of sorts? All right. Number theory. I'm already making mistakes. Okay, and so sort of the basic plan for us is we're going to very loosely, but much slower, much slower, cover some topics from Zanier's, some problems in unlikely intersections, which by now is a little outdated, but only a tiny amount, written about 10 years ago. And specifically, we'll be sort of gearing towards understanding sort of a bunch of work that's been done on the Andre-Urd conjecture and related material. None of this is stuff you have to know yet. It's just a sense of where we're going. All right, so let me start with sort of where the subject, I think, typically starts, which is a result of Lang. So the result says the following. Sorry. So we'll be talking about Lang's conjecture, which by now is a theorem. So we're going to understand the following thing. So consider a polynomial p in two variables, x and y with complex coefficients. And we're going to be interested in solutions. So xc1 and xc2, which are roots of unity. So some power of xc1 and some power of xc2 is equal to 1. With p of xc1, xc2 equal to 0. Okay? And so you can sort of write this in the following way. You can write this as there exists n1 and there exists n2 such that xc1 to the n1 is equal to 1, xc2 to the n2 is equal to 1, and p of xc1, xc2 is equal to 0. Okay? And so this is sort of a prototypical example of what in the subject we consider an unlikely intersection, because we have two variables, c1 and c2, two complex variables, and we sort of have three equations for them. This one, and this one. Now, if we just had sort of a fixed n1 and n2, we sort of would get finitely many solutions, sort of assuming things aren't too degenerate in some ways we'll talk about precisely. And that would be the end of the story. What makes the whole subject difficult is you have this countable union outside over integers, over pairs of integers in this case. Okay? So you have sort of a countable collection of problems, each of which you expect to have no solutions, but there's infinitely many of them, so it's not really clear what sort of happens. So the question is sort of when, I'll put this up in a second, when are there infinitely many such solutions? Okay. So this is sort of the first question we'll be interested in trying to understand. So it's actually, it turns out, even though it's sort of written up there in somewhat fancy language, this question is fairly classical in that it dates at least like maybe 50 years back. So this is very related to trig polynomials, trigonometric equations, sort of. As an example, sort of a prototypical example, you can look at the equation cosine 2 pi, I forget, is there an n? 2 pi x plus cosine 2 pi y plus cosine 2 pi z is minus 1. Here we have three variables, there we had two, but we'll get to three soon enough. And sort of this thing is related, so rational solutions to this equation are related to classifying finite subgroups of PGO2C. Okay? And I'm not going to go through it, but sort of the idea is that you look at transformation, you look at the eigenvalues for it, you get roots of unity. Because you're finite, you get some equations. This thing turns out to be quite prominent. This was studied, in case you're interested, by Gordon, 77. He studied this equation. And if we look at the rational solutions in x, y, and z, this is sort of evidently a case of what we're looking at here. What you can do is you can let xc1, xc2, and xc3 be e to the 2 pi ix, e to the 2 pi iy, e to the 2 pi iz. And if x, y, and z are rationals, that exactly means xc1, xc2, and xc3 are roots of unity. And so if you sort of, you can rewrite this equation as xc1 plus xc1 inverse plus xc2 plus xc2 inverse plus xc3 plus xc3 inverse is equal to minus 1, minus 2, thank you, correct? No, nothing back here. It's minus 2, and this is not a polynomial, it's got this sort of inverse guys we can multiply through and get a polynomial. And in fact, it turns out to be most natural to just allow inverse monomials. So we're going to look at LaRonde polynomials from now on. It sort of makes the whole theory much nicer. Okay? Okay, so let's look at examples now. So what's an example of a polynomial which sort of clearly has infinitely many solutions in roots of unity? The simplest example is P of xy is, maybe the simplest one is like x minus 1. So if x is 1, y can be anything. That's infinitely many solutions right there. More generally, you can take x to the m, y to the n minus 1. M and n are at least 0. Right? Because then if x is the root of unity and you solve for y, y will be root of unity as well. You can also take x to the m minus y to the n. M and n are at least 0. And in fact, it's sort of, if we allow negative coefficients, these are really the same equation. So if we can sort of divide through by y to the n, if we think of that as a unit, these two are the same. So sort of the most general case in this style is you can look at x to the m, and not minus y to the n, but minus xi y to the n, where m and n now we allow to be arbitrary integers. Let's say not both 0, because that's kind of silly. And xi is the root of unity. Okay? So then these polynomials are examples where you have infinitely many solutions in roots of unity to P. Is this clear, everybody? 3 examples? Okay, so the idea is we're sort of, being the root of unity is a multiplicative relation, so as long as our polynomial expresses that multiplicative relation in some natural way, we get infinitely many solutions. All right, so then the theorem in this language, due to Lang, basically says that these 3 are the only cases, or maybe this one, this language, is the only case where you have infinitely many solutions. So it says if, let's say, P of xy, which, as I mentioned, it sort of becomes easier if you allow LaRonde polynomials. So we're allowing negative monomials as well. It has infinitely many solutions. In roots of unity, then is divisible by one of these guys. So this divides P of xy for some mn integers, not both 0, and some xi, a root of unity. Okay? So clearly, if it's sort of divisible by one of these guys, it has all the solutions, you get infinitely many. Otherwise, the claim is you get only finitely many. You can sort of get more greedy, and, well, you can get more greedy in like a couple of ways, right? One way to get more greedy is you can ask for, well, finitely many is still bad, let's look for the ones with no solutions in roots of unity. That can be shown sometimes. We'll sort of maybe review a couple cases where you can do that. But in general, that's sort of, I don't know, it's very hard to do that without explicitly ruling out solutions. Like, it's hard to rule out 1, 1 without saying P of 1, 1 is not 0 or something. So that ends up being a little difficult. The other thing you can ask for is you can ask for an effective bound for the number of solutions. And that's something to be concerned with a lot. Right? It's one thing for me to tell you it has finitely many solutions in roots of unity. It's another thing for me to tell you it has at most like 1 billion solutions, or some number, depending only on P. And it's yet a third thing for me to tell you here is a finite set of computations which will produce for you all the solutions. So these three are genuinely different requests, and we'll sort of pay attention to them from time to time. But for now, sort of this is like a good example of the kind of thing we'll be after in the course. We have some sort of special arithmetic relation. We want to get some sort of finiteness theorem. You have some special structure that accounts for our results not being finite. All right. So we're going to prove this theorem in a number of ways. But before we do that, let's sort of re-express it in more algebro-geometric language, because in this case it sort of will explain to us how to generalize, and sort of, I think it explains where the structure comes from a little better. So consider the set V sub p, which I'm just going to mean the zero set of pxy equals 0, which I'm going to think of as a subset of C star squared. Okay? This is another good reason to allow 1 over x, 1 over y, because that's sort of the ring of functions on C star squared. That's the ring of regular functions here. And this guy is actually a group. It's not just an algebraic variety. You can actually multiply elements together. And the multiplicative structure is clearly important to us. Okay? So one way in which we won't use very heavy algebraic geometry is sort of a proper algebraic geometer would care about the nilpotents in this sort of scheme and such, and we're not going to care about that stuff almost ever in this course. We're only going to care about sort of subsets of complex numbers. Okay, so this is an algebraic group, clearly, but which just means it's an algebraic variety, and it has a multiplicative structure. And if you look at V sub x to the m minus y to the n, so you look at a subvariety where x to the m equals y to the n. So it's obviously a subvariety of C star squared, but it's also a subgroup. If you multiply two solutions here, you get the solution. So this is what I'm going to call, sort of in a very naive sense, an algebraic subgroup of C star squared. Okay. Moreover, if you look at the sort of pairs of roots of unity, so let me just write it concretely. So if you look at pairs sigma 1, xi1, xi2, or what am I writing? Zeta 1, zeta 2, I guess, where zeta 1 and zeta 2 are roots of unity. Well, this is exactly the torsion subgroup of C star squared. Right? So I'm going to write this as C star squared times 2 for squared sub tor. Tor for torsion. It's exactly the torsion elements inside C star squared. Which means that this guy over here, x to the m minus xy to the n, well, this actually isn't an algebraic subgroup, but it's sort of the next best thing. Sort of, this guy isn't a subgroup, but it's a torsor for this group. If you take any element here, and you multiply it by any element here, you get another element here. So just thinking in terms of sets and points, you can write this as zeta to the 1 over m comma 1. Sorry, yeah. So just pick an mth root of zeta, and so this gives you a point. And now multiply it by v sub x to the m minus y to the n. And this will, in fact, be exactly this set. Okay? So it's a translate of an algebraic subgroup by a torsion point. So, in fact, it's an algebraic group. Sorry. There's no so, in fact. This is the end of the sentence. Translate of a subgroup by a torsion point. Okay, so we're going to call this thing a torsion coset. So it's, in other words, it's a torsion point times an algebraic subgroup. Okay? So we're just sort of restating things so far. There's not very much content to any of this. Okay, but now using this language, and the language is sort of varieties, we can restate that theorem up there in sort of maybe a nicer way, or a more generalizable way. So theorem, so this is Lang version 2. If you go to any paper on the subject, they'll sort of start with maybe 3 or 4 statements of Lang's theorem. So you can get a whole bunch of other ways to look at it. But here's a fairly innocuous restatement. So we're going to start V in C star squared as an algebraic variety. So it'd be an algebraic subvariety. I think in the future I'll remove the word algebraic, but this is a subvariety of C star squared. So then either V contains a torsion coset, or V intersect the torsion points of C star squared is finite. Okay? So we're literally sort of restating that theorem, just replacing the zero set of P by the variety V, and replacing the division by a containment of a subvariety. Okay, and now I'm going to restate it one more time, and then we'll get down to actually doing some mathematics. And this time our restatement will, as its fundamental object, use the torsion points, not the varieties itself. Let me explain what I mean. So let me call it T1. Let this be a sequence of distinct elements of C star squared, all of which are torsion. Okay? Here we're talking about start with a variety, which torsion point does it contain? Here we're starting with just a sequence of torsion points in C star squared. And what we're going to do now is let V be the smallest. Whoa, how did this board get here? So we're going to let V be the smallest algebraic variety containing all of these guys. So be the smallest algebraic variety in C star squared containing okay? And there is a smallest guy, because if you have 2, you can intersect them, and eventually it's to stabilize, containing all of these guys. So in other words, a sort of more concrete way to write this is V is the Zariski closure of the union of all these points. So in the Zariski topology, where you only have sort of the only closed sets or the closed subvarieties, is the smallest, is the closure of the union of these points. Okay? But this is not so important. This is literally what I mean. Then either V is all of C star squared, right? You can certainly be Zariski dense. Or V is a finite union of torsion points and torsion cosets. Okay? So I claim these two are equivalent statements, right? So what's the proof? Well, suppose you had that top one. Now, if V isn't one of these things, that means it contains some curve, which is not a torsion coset, and that curve has to contain infinitely many torsion points. Otherwise, you have a smaller V, which has replaced that curve by the finitely many torsion points. That's a contradiction. And suppose you had this theorem, then if that V had infinitely many torsion points, well, look, there's a risky closure. It's got to be some curve, and it can't be V because V was not a torsion coset. That contradicts the statement right here. Okay? So in fact, these two are equivalent statements. It's a good thing to convince yourself of. All right, so I really like this statement because it's sort of, what it's really saying? It's saying, well, in C star squared, you have there's a risky topology, which sees all algebraic varieties, and you have the smaller topology just of torsion cosets, of like torsion points, torsion cosets, and C star squared. And it's sort of saying that if you just start with torsion objects, you can't see anything but torsion cosets into the risky topology. It's sort of closed in a certain natural sense. By taking sort of closures in the risky topology, you can't get sort of bigger elements. All right? Okay, so these three are equivalent way of saying the same thing. All right, so eventually we'll go to higher dimension and sort of try to understand the story there. But for now, let's start on the proof of this theorem. Probably won't finish today. So, sort of all proofs actually that I know of this theorem go through a step which is reduction to arithmetic. Okay, this is a very common step in the subject. So note we're starting with a polynomial, well, over here, we're starting with a polynomial with complex coefficients. And somehow we're going to say that, well, it's really enough to look at q-bar coefficients. The complex coefficients case doesn't actually add anything. Okay? There's a few ways to do this, but we will use Galois theory. So first of all, without loss of generality, we can assume irreducible. P of xy is irreducible as a polynomial. Okay? Why? So proof, well, the proof is very simple. It's if P of xy factors into two different guys, then the zero set of P is just the zero set of P1 union the zero set of P2. And then if this guy has infinitely many torsion points, this guy, then one of these two must as well, and then we can just work with P1 or P2 instead. Okay? So we're going to assume that P of xy is irreducible, and then we're going to make the very key observation that the roots of unity, the torsion subgroup of C star, actually lies inside Q bar. Okay, very important. In fact, it lies in the smaller fields because they're all abelian over Q bar, and that's sometimes important. But for us right now, we're just going to care about Q bar. Q bar is already a much more accessible thing than C. Okay, so now we're going to pick an element sigma of the Gallo group of C over Q bar. I'm not sure it's legitimate to call this a Gallo group. Many people call this an automorphism group or whatever because it's not an algebraic extension, but some people call it a Gallo group as well. So I just mean field automorphisms. C C over Q bar. And C is algebraically closed, so it's got many automorphisms over any subfield. Okay? It's now going to define an action of C. So there's an action of the Gallo group, in fact, of C over Q. This acts on polynomials, or even on Laurent polynomials, just by acting on the coefficients. So sigma of the sum of aij x to the I, y to the j. We're allowing I and j to be negative as well as positive, and it's a finite sum. We're just going to define this to be the sum of sigma applied to aij x to the I, y to the j. So it's a fairly innocuous definition. And it's kind of nice because with this definition, P of, well, let me not call it xy, P of AB equals 0 is exactly true when sigma P of sigma A, sigma B is equal to 0. Right? Precisely because sigma P of sigma A, sigma B is sigma of P of AB. Okay? Questions about this? Okay, so now, one more time, so recall, it's now, we again have sigma in the Gallo group of C over Q bar, not just over Q. And now because all roots of unity are in Q bar, if sigma 1, if zeta 1, zeta 2 are in the torsion subgroup, and P of zeta 1, zeta 2 is 0, then sigma P of sigma zeta 1, sigma zeta 2 is 0, what we just showed, which means that sigma P of zeta 1, zeta 2 is 0. Right? Because sigma fixes zeta 1 and zeta 2, it in fact fixes all of Q bar. Okay? That's sort of the point. The point is we started with one polynomial, which was 0 on these guys. And if it's not defined over Q bar, we're going to get a second polynomial, which is 0 on these guys. And two polynomials and two variables don't have all that many roots in common. Okay? Okay, so now, if P and sigma P don't divide each other, remember, P is irreducible, so sigma P is also irreducible. So if they aren't like the same irreducible factor up to a constant, then the intersection of their zeros is a zero-dimensional variety, and this is actually a finite set. You can actually see this without talking about varieties. You sort of have two polynomials in x and y. You can treat them both as polynomials in x with coefficients, which are sort of polynomials in y. And since they're reducible, you can reduce them. You can sort of take a linear combination with Euler's algorithm and get a polynomial in y. And so you know that any common zero, there's only finitely many possibilities for y, and then you get finitely many possibilities for x as well. But in fact, if you're willing to go a bit stronger, you can use Bézout's theorem, which I'll mention again later. But even at this point, you can use Bézout's theorem to say that not only is this intersection finite, but in fact its size is at most the size of the degree of P squared. Okay, which is pretty good because as far as the effectivity thing we cared about earlier, now we're not getting just a finiteness claim, we're getting an actual bound for the number of points. Okay, though we're still not explaining how to find all the points. Okay, so if this happens, we're done. So if it doesn't happen, P has to equal some constant times sigma P. Some complex constant. Now, without loss generality, we can scale P by complex numbers. That doesn't actually change anything. We can assume one of the coefficients of P is 1. Just take some non-zero coefficient and scale it to be 1. And then sigma P also has the same coefficient be 1. So that means that C sigma has to be 1. Okay? And this is true for all sigma. So the coefficients of P are fixed by all the automorphisms of C over Q bar, and it's a basic theorem in Gallo theory, infinite Gallo theory, that this implies that in fact P has coefficients in Q bar. Okay? Any questions about the argument? So if you haven't seen sort of this before, I suggest you brush up on some infinite Gallo theory. It's not very long proof, but it's important to sort of to understand that in fact automorphisms of C over Q bar, even though it's a transcendental equation, there's enough of them to detect all of Q and nothing bigger. Okay, so once you sort of get used to this technique, it's a very common and easy thing to apply, but it's actually quite powerful because it allows us to go from the world of the complex numbers to just the world of arithmetic, which is a much kinder world. This eraser is making a bad sound. Yes, as I mentioned, sort of pretty much all the proofs I know start this way. And now there's sort of a number of ways to proceed. What we're going to do at first is we're going to proceed using measure theory. And so we'll review some of that in a minute. But here's sort of the idea. The idea is let this sequence of SIs not be the points of V. Sorry, I'm missing a step. Let me go back. Before we do that, I'm missing a step. Okay, so we have P in Q bar. And so one of the good things about Q bar is if you add any finitely many elements from Q bar to Q, you get a finite extension of Q. Because every element just generates a finite extension. And so therefore, P of xy is in K adjoin this guy for some finite K in Q bar. And again, you can just take K to be Q, adjoin the coefficients of P. So in fact, you could work with K, but it's sort of often more convenient to work with Q here. And there's a nice trick instead of K to work with Q at the cost of irreducibility. But it's still often worth doing. So what we can do now is we can do this quite basic trick where we define Q of xy just be the product over embeddings from K into Q bar, and there's sort of the degree of K many of these, of the conjugates of P. Okay? So P has coefficients in K, and just take all their Gallo conjugates. And because we're taking all of them, you can show that this thing is invariant under the Gallo group of Q bar over Q. We're sort of not preferencing any one embedding. And so as a result, this polynomial, while not being irreducible over C, though it is irreducible over Q bar, over Q, has coefficients in Q. Okay? From an algebraic geometry perspective, we're taking our variety of zeros of P, which is not defined over Q, but is defined over K, and we're taking the union of its finitely many Gallo conjugates. And that gives us a non-irreducible variety, but it's defined over Q. You can sort of sometimes want to do this, sometimes you don't, but it's a good thing to keep in mind. So we are going to do this. And then the point is that if you look at VQ and you look at the torsion points inside VQ, then because the polynomial Q is defined over the rationals, this is fixed under the action of the Gallo group of Q bar over Q. Okay? I see. Okay, so again, just to recap, first we sort of start with the complex numbers, and we show that if you're not over Q bar, well, that's sort of silly. You should really be over Q bar. You're not sort of, you just have extra structure going on otherwise, which we can exploit. And if you're over Q bar, you're automatically over some finite extension, and by some sort of easy trick, you're over Q. What's the point of being over Q? It means if you have one root of unity, you have all its Gallo conjugates as well. So that's quite nice now. Starting from one point, automatically you get a whole bunch of others. If you think about it, it's sort of, how to say, it should make you feel much better. Because a priori, you could have had a very sporadic set of roots of unity in your variety, right? Like roots of unity of order like 1, then a billion to the power of a billion. And it's very hard to work with all of these together. But now you know if you have any one of order a billion, you have sort of all its Gallo conjugates. And that's quite a lot. And so now you have sort of a very related family of roots of unity to work with. So somehow that should make you feel happier, even if you don't know what to do yet. Okay, so now that we're fixed under this guy, back to what I was saying. So let these guys not be just the points here, but we're going to group the points together under the action of the Gallo group. So these guys are these orbits of the roots of unity inside the variety VQ. Okay? Okay, so now the argument we're going to use, and it's surprising how applicable this is like I said, a measure theory argument. So we're going to show that these Gallo orbits, unless they're constrained to sort of a torsion coset or to finitely many torsion cosets, in fact, they sort of jump around all over the place. And what do I mean by all over the place? Well, clearly they're all sort of absolute value 1. So in C star squared, they're all inside S1 squared, or inside the unit circle squared. But in fact, they sort of become equidistributed inside the unit circle squared. In any region, there's as many of them as you would expect. So we'll review what that means. But let me just say that in sort of a formal way. So to every one of these sets, I'm going to assign a measure, delta S, which is the general thing we'll be doing. which is 1 over the size times the sum over all the points in S of the delta measure of that point. So recall, what should a measure be doing? What's its job? Its job is to take in a function, maybe with compact support and continuous, and return a number. It should let us integrate functions. That's sort of what a measure does. And that's what this thing does. If you integrate a function with respect to this measure, literally all you're doing is you're averaging it on these points. Okay, so sort of formally, the integral of f with respect to delta S is by definition the average of the sum of f of p of p in S. Sorry, this is a different p than above already. We've left that p behind. Maybe I'll change my p's to t's so it's not confusing. Okay? And so now we want to say that unless there's some sort of torsion coset structure going on, these guys spread out as much as possible. So claim if for any torsion coset V in C star squared, only finitely many of these guys are in V. Okay? Because clearly if they're all in V, then they can't spread out everywhere. They're constrained in V. But if they're not, then this sequence of measures converges in the weak star sense, which I'll review, but in some measure theoretic sense, converges to the Haar measure on S1 cross S1, which I'm going to call mu sub S1 cross S1, which is really what you think, sort of d theta 1, d theta 2 divided by like 4 pi squared or something. Okay? Okay, so we'll sort of, again, recall what this is in a minute, and we'll, okay, maybe we'll prove this next time. But sort of why does this do it for us? Well, it does it for us because by assumption, let me also call this, well, I guess we don't have it, it's fine. Sort of by assumption, all of these SIs lie inside VQ. Right? And VQ is a proper subvariety. It certainly can't contain all of S1 cross S1. So all of these points are even constrained to like a closed subset of S1 cross S1. They can't even go everywhere, let alone be dense as a measure. Okay, so that's the idea. It's kind of, sort of, at first glance, it looks like overkill, because all we have to show is that these points can't lie inside the subset. In fact, we show that not only is that not true, but they spread out everywhere. But it's sort of a miracle that, in fact, this claim is often much easier to prove than just sort of the containment claim. Okay, so we'll review all that next time. Any questions? Of any sort? Yes?
Wondering why the S1 and S2 why are those orbits finite?
Oh, why are these finite orbits? No, that's a good question. So the point is, they're all inside Q bar, their coefficients. And any algebraic, what does it mean to be algebraic? It exactly means you have only finitely many conjugates. Right? That's sort of one of the main points of getting into Q bar, is that somehow reduced to finite objects right away. We use the same trick up here, where instead of being in Q bar, we're inside K. Some finite extension. Other questions? All right, so now I'll see you all on Friday. And yeah, so most of the time we'll be just meeting just upstairs in the library. Only a couple of times there's a conflict and we're meeting down here. But if you show up the fields at 2, I'm sure you'll be fine. Right. Thanks. Oh, 1. Sorry. Show up the fields at 1. You'll be fine. It's 2 right now. Yes. 1 o'clock.